Greeting to everyone. The work I'm going to present has been developed in the framework of a collaboration between the Politecnico University of Bari, the C2N CNRS of Palaiseau, and the La CNRS of Toulouse. The average age of the world's population is increasing linearly, and an increasingly old population may face the natural, functional, physical, and cognitive decline that may come with age. This can find relief, of course, in new technological solutions devoted to improving the quality of life. Some application areas have considerable importance in promoting active and healthy aging within its own environment, such as those related to health, navigation, and safety of frail individuals. And human-machine interfaces and augmented reality can be precious, of course, in case of cognitive impairment, being able to effectively present visual information in support to understanding and decision-making. Visual text stimuli can help with word finding during conversation and generally to improve decisional capacity, especially in mild to moderate cognitive impairment. The first augmented reality wearable system was proposed in 1968 by Evan Sutherland and was given the moniker Sword of Damocles because of its weight and of the fact that the system was partially hanging from the ceiling. Since then, other systems with progressively smaller sizes, lighter weights, and better wearability in general have been presented. Near-eye display can be obtained by exploiting either half mirrors, waveguides, refractive freeform optics, in combination with projectors, as well as with pin light and holographic approaches. Near-eye displays can be designed by exploiting the metalenses paradigm. Metalenses, which are basically metasurfaces, promise to overcome the angular spectral limitation of purely refractive structures while offering extremely smaller form factors. Here, we want to exploit guided mode resonances to design a near-eye transparent metalens that can selectively reflect at least two colors, for example, red and green, in order to effectively represent information. Dielectric grating for reflecting a single color have been demonstrated in a number of studies. And also multiple guided mode resonances have been demonstrated so far in the near infrared. For the application we have in mind, in which we want to represent simple visual text information, we don't need a huge eye box, thus the half mirror approach is a good point to start with. So we need basically a transparent supporting surface, such as spectacle lenses that must be sufficiently reflective for some specific desired wavelength and transparent for the remaining part of the visible spectrum. This would allow the desired information to be presented to the observer without compromising the colorimetric perception of the scene. The visual information is then projected on the display by means of a laser or an LCD projector. The human eye has three types of photoreceptive cells, known as cones, which are sensitive to blue, green, and red light, respectively. The cones' activation levels, namely the stimuli, allow any color sensation to be described. Here are shown the so-called three-color matching function associated with the cone sensitivities of a standard observers. Perceived color can be then encoded through a triplet of x, y, z values called the tristimulus, which can be calculated by weighting the spectrum of light striking the eye against the chromaticity matching function. This can be then converted to more common format, such as the RGB format. A light spectrum consisting of a single spectral line will correspond to a perceived color that depends both on its spectral position and on its width. For narrow peaks, the colors are hypersaturated and located on the outer contour of a CIE chromaticity diagram. As the line width increases, the color becomes less saturated until they collapse within the primary color triangle with a very desaturated and dull effect. Therefore, peaks having a width smaller than 75 nanometer are needed in order to represent color correctly. In the studies, we are proposing a new metalens design that exploits guided mode resonances. The structure consists of a silicon nitride grating placed on top of a waveguide core of the same material, both placed on a glass substrate. Here, the grating acts as a phase adapter between the incident wave and the modes supported by the guide, allowing guided modes to be excited by direct illumination. A resonance arises when the guided mode is excited, which happens exactly when the incident wave vector component parallel to the grating equals the sum of that of the guided mode plus an integer multiple of the grating wave vector. This means that the effective refractive index of the excited mode must satisfy the equation indicated by the green arrow in the slide. The figure on the right shows the dispersion curves for the TM mode supported by the structure for specific core thicknesses. This curve, which have been calculated analytically, and the black line represents the requirement for the effective index in order to obtain a guided mode resonance. The structure meets this condition at the points highlighted by the yellow circles. To understand how the metasurface works, we simulated the structures by means of the right-coupled wave analysis method, varying each geometrical parameter at time. Here are some of the results of the simulation, which show how the reflectance of the metasurface changes as we vary the grating thickness, the duty cycle, the polarization angle, and the angle of incidence. In particular, we see here the reflectance maps as a function of the wavelengths and of a single geometrical parameter. We observe that for grating thicknesses lower than 150 nanometer, the effective waveguide acts as a monomodal waveguide. Thus, we fix the thickness of 100 nanometer, where we observe a well-formed peak with an intensity close to unity. And we do the same with the duty cycle. Here, the reflectance peak is maximized for values close to 60%. Besides, we observe that for a non-zero angle of incidence, the resonance splits into two distinct branches due to the removal of the degeneracy between the propagative and the counter-propagative modes. On the lower right, we see that by modifying the polarization angle, we can select a different set of guided mode resonances, namely the TE and the TM modes, while for intermediate angles, there is a combination of the two sets of modes. In other words, the reflectance of the metasurface can be tuned by varying geometrical parameters. This allows us to design a metasurface with the desired reflectance properties. If we increase finally the period of the metasurface, we observe a peak of the reflectance spectrum that shifts toward longer wavelengths. And this shift is about of 1.3 nanometer for every 1 nanometer increasing period. Below the map, we see the corresponding palette of the perceived, reflected, and transmitted colors for the different periods. The reflectance palette show good saturation of color, while the transmittance palette show very pale and dull color. Both of these factors are important, in fact, when choosing the final design of the metasurface. To ease the identification of optical solution, we can take advantage of a definition of a cost function f, which is defined as the sum of the minimum distances between the resonating wavelengths and the target wavelengths we want to excite, identifying the primary colors blue, green, and red. The figure shows the logarithm of this cost function, and the blue, green, and red curves identify the loci in which the structure has a peak in reflectance centers exactly on the corresponding color. Oops, sorry. The bichromatic solution able to excite both green and red are highlighted with circles, while trichromatic solutions are highlighted with this special hexagonal marker. The table on the left shows the geometrical parameter corresponding to the trichromatic solution for the TM modes, and when we consider an incident angle of 45 degrees. Let's look at an example of a bichromatic solution. On the left side of the slide, we see a reflectance map as a function of the wavelength and of the core thickness of the structure. This map is calculated for a period of 240 nanometer and for T polarization, which is a solution for the order -1 of the grating. The vertical lines, the limits are 10 nanometer tolerance intervals around the wavelength corresponding to primary green and red colors. As the core thickness increases, a larger number of resonance appear and redshift. And when the core reaches a critical thickness of 480 nanometer, two distinct reflectance peaks fall simultaneously within the desired intervals, with an amplitude close to 19 and to 99%. We then calculate the perceived reflected color and transmitted color and the corresponding chromaticity diagram, and we consider standard white light for transmittance, and we shine a filtered 10 nanometer white source centered on each peak in order to calculate the reflected color. We obtain a very saturated and intense green and red color in reflection, as well as a fairly neutral transmittance, which is very close to the point labeled D65 in the chromaticity diagram. Therefore, this solution does not substantially change the color of the field of view observed through the lens and ensure a well-saturated reflection of the red and green colors. Polychromatic solution can be found for other combination of geometrical parameter as well. For example, the figure on the left shows a trichromatic solution, which is obtained for a period of 513 nanometer and a core region thickness of 452 nanometer for TM polarization at 45 degrees of incidence. The figure also includes the CIE chromaticity diagram, which shows the position of the perceived color when the structure is illuminated with a filtered source centered on each resonant peak. In addition, a very bright, in addition to this very bright and saturated color, we found fairly neutral transmittance at normal incidence with a very slightly yellow-orange tint. The figures on the right show two other solutions, a pentachromatic and an hexachromatic solutions. This solution allows the selective reflection of a larger numbers of the side color, basically. Finally, I will show you an experiment that demonstrates the proposed metalens. We fabricated a first sample of the metalens at La CNRS of Toulouse in France, and we use our design having a period wide enough to be easily made using electron beam lithography. This design has two sets of resonance for TE and the TM mode that are close together, and we fabricated a square sample with a side of 500 microns, and it was fabricated by depositing silicon nitride on a glass substrate using chemical vapor deposition technique. Then we used electron beam lithography and dry etching in order to create the grating, the pattern. Here we see an optical microscope image showing that some flows are located at the edge of the vertical field stitching region of the beam process. However, the sample pattern seems fairly well defined. On the right, we see an image of the sample that shows a vivid, highly saturated red to green reflection as the angle of incidence changes when illuminated by polarized white light. We use an EP4 Accurion ellipsometer to measure the refractive index and the reflection spectra of the silicon nitride sample. We measure the reflectance at an angle of 45 and 50 degrees. And the dashed curve in the figure shows the simulated reflectance using the measured silicon nitride indices, which includes dispersion. The solid curves show the measured reflectance at the zero order. And the measurement shows peak with intensity of about 50% for the TM modes at 45 degrees and of about 60% for the TE mode at 50 degrees. The peak have a width of about 12 to 20 nanometer. And in addition, the transmittance at normal incidence shows an overall transparency of about 77% for the TM polarization and of 68% for the TE polarization. Overall, the experimental results demonstrate that the proposed metalens is a viable design. It has a good reflectance and a transmittance, and the reflectance peak are narrow with a fairly good intensity. However, when modifying the measurement position along the sample, is it possible to observe some variability in the spectral position of the peak, which suggests a slight variation in fabrication parameter along the sample. In conclusion, I show you the design of an optically transparent metasurface based on guided mode resonance devoted to augmented reality visual aid in support of individual with cognitive impairment. We saw the design of a bichromatic to polychromatic metalenses with good transparency in transmission and good color saturation in reflection. Future efforts will be devoted to the fabrication of a second generation of samples and their complete characterization with a goniometric optical setup. It will also be necessary to assess the performances of this metalens in terms of other parameters such as resolution, field of view, and eye box that are important in near-eye wearable augmented reality system. So I would like to conclude, to acknowledge the project Research for Innovation, namely REFIN, within which the presented activity was carried out. I want to thank you for your attention. If you have any question or curiosity about this work, a greeting